expressions for the rotations of the cross section. Once we are done with that, we look into how we could represent strains, especially for beams. So of course we will derive the 3D strains in terms of the general displacement and rotation parameters, but eventually we'll express those 3D strains in terms of the so-called 1D strains, many of whose components we've already introduced in the previous classes. So just let's recollect what we did at the end of last class. So it's a repetition of the last slide from the last class, which is the Euler's theorem for rotation. If you recollect, we had said that basically the Euler's theorem of rotation helps us to consider any rotation between an initial orientation and a final orientation to be a so-called simple rotation, whereby we just need to know a particular unit vector or a direction about which this rotation takes place, overall rotation, and the magnitude of that rotation, which is basically the angle which is involved. But the fact that that direction can be specified by a unit vector means that you don't have all of those three components of that vector as independent. You have a constraint which enables that. So Euler proved that a minimum of 4 scalars are needed to describe the rotation free of singularity. Some people attribute this discovery to another researcher, but in most of the standard literature it remains to be called as Euler's theorem, so we'll continue to do that. But basically, once you know that there is a constraint, you know that there is going to be only 3 independent quantities here to describe the rotation. But if you eliminate one of those 4 in whatever way you want, then basically you end up with a singularity, and that's always the case. And in terms of these 4 quantities that we have introduced, namely E1, E2, E3, and the angle alpha, which is the magnitude of rotation, or the E1, E2, E3 expressed as a single column matrix E, we can then describe the direction cosine matrix of a rotation from a frame or a rigid body B in A. So that can be expressed in the form of this particular equation. I think I missed out expressing this at the end of last class. That's why I thought of repeating this particular slide. So here delta is the identity matrix, which is a 3 by 3 identity matrix, and then you have the cosine of alpha as scalar quantity, then E times E transpose multiplied by 1 minus cos alpha. This will of course end up in a 3 by 3 matrix, E into E transpose, and that's again multiplied by a scalar quantity which is a function of alpha. And finally E tilde, an antisymmetric matrix over here, multiplying another scalar quantity sine alpha. So this gives an expression for the direction cosine matrix in terms of these 4 parameters, namely E1, E2, E3 and alpha. So this is one way of expressing it, the rotation in terms of these 4 quantities, and then expressing the direction cosine matrix in terms of those 4 rotation parameters.
So this is simple rotation?
For all rotations can be expressed as simple rotations. So that is Euler's theorem of rotation. That basically any rotation between the initial and final, though the intermediate stages can be whatever, the final and the initial can be compared to each other, and you can always identify a single axis of rotation, and that will be parallel to this particular vector, unit vector that you have. Okay, here of course is expressed as a column matrix, but the corresponding unit vector that you have E is basically what is the axis of the rotation. Okay, and alpha is the angle around magnitude of the angle around that particular axis that the body B has rotated in the frame A.
Sir, is this formula an exact analytical formula, or
it is an exact analytical formula, yes.
Or truncated terms of a series?
No, it is not. It is not. In fact, we will look at certain other ways of parameterizing the rotation, where we will see that there is a truncation. So this is something which is exact analytical, and so can be used for any large rotation, however large it might be. And the other interesting thing is it doesn't have singularity because you're still having 4 parameters here. So you can see that this will never blow up, for example. So theoretically it is valid from minus infinity to plus infinity value of alpha. So that's one of the advantages of using this kind of representation, though you have to deal with more number of variables, 4 instead of 3.
Having a singularity means what?
Having a singularity means, for example, some of these terms will blow up. For example, if instead of the sines and cosines it involved, let's say, tan alpha, then at alpha is equal to 90 degrees, tan alpha would become 10 to infinity, right? So it blows up. So something like that will happen. There are certain values of these angles for which certain of the quantities which help in the parameterization will not be determinable. Okay, so we'll see some examples of those also, because this is not the only representation or parameterization of rotation that we will be using. There are other parameterizations also, with the advantages and disadvantages differing from what we have here, and in those cases I'll point out to the singularity. Yes.
That means, sir, here we won't have this. If we express this in terms of only E matrices and except this alpha, we replace it with somehow with this E1, E2 or E3, something like that. Then that will be a like a singularity expression possibility here.
See, in this particular set of 4 that you have, alpha, E1, E2, E3, you may not be able to eliminate alpha, but you can eliminate one out of these 3 by using this particular equation, E1 squared plus E2 squared plus E3 squared equal to 1. Once I eliminate that and put everything in terms of E1, E2, you will see that it will so happen that in this particular equation you will end up with a singularity. Okay, you can try it.
Possibility of singularity remains.
Exactly. Not for all, there will be certain values of alpha for which things blow up. Okay. Another way of looking at it is to look at the direction cosine matrix itself as a parameterization of the rotation. So it has 9 components. So instead of dealing with 4 components here, I can just deal with 9 components there. Okay. So there again you have the orthonormality, because of which CBA into CAB should be equal to the identity matrix. But CBA into CAB will always result in a symmetric matrix. So you will not have 9 independent equations, but you will have only 6, 3 coming from the diagonal elements all equal to 1, and 3 coming from the off diagonal elements all equal to 0. So you will have 6 equations and 9 quantities. So it will become just 3 independent quantities once again, which is exactly what Euler's theorem of rotation also says. But even in that situation, if you eliminate, use those equations to eliminate, you will end up with a singularity.
So, scientifically speaking, we just need the direction and the magnitude of rotation.
Exactly.
Where does the singularity fit in?
No, see, you need a direction, but the direction can be expressed typically just in terms of 2 quantities. When you do that, you will end up with, you try to do that. You just use this particular equation. Let's say you take E1 is equal to now minus square root of E2 squared plus E3 squared, right? So 1 minus, right? So you can utilize that and see that you will end up with a singularity. Okay. So you could just rederive this and then you can see where the singularity drops in. Okay. But that's basically Euler's discovery, or actually in fact it's not Euler's, but it's attributed to Euler. That he discovered that though there are only 3 independent quantities, because he was the one who stated that every rotation between a final and an initial orientation can be expressed as a simple rotation. But the fact that it is free of singularity is something which was discovered by somebody else, but is also attributed to Euler. But basically it is rigorously proven that whenever you eliminate, however you eliminate the 4th variable that is involved there, you will end up with a singularity, and as I said, we will see some examples of that. Okay, let's let's see the fact that the Euler parameters, when they are used, they reduce the nonlinearity level. Okay, let's see how that is done. So from the previous slide, I just repeat this equation of the direction cosine matrix in terms of the E and the alpha. Now we introduce certain trigonometric manipulations we'll use the multiple angle formula. So cos alpha is equal to 1 minus 2 sine squared alpha by 2. Same thing again is used over here. So the 1 minus 1 cancels and it is 2 sine squared alpha by 2. So that same formula is used in the first two terms. In the third term, again we'll use the multiple angle formula for sine alpha as 2 sine alpha by 2 cos alpha by 2. Okay. So once we do that, we will now replace the sine alpha by 2 and cos alpha by 2 in terms of certain quantities, which is what Euler used. And in some literature they are called as the quaternions, because we'll express it in terms of 4 different parameters so that we'll avoid the singularity. So these are either called as Euler parameters or as quaternions in various literature. The first 3 are basically associated with sine alpha by 2, and the E1, E2 and E3, which are the components of the unit vector about which that simple rotation takes place. And epsilon naught is basically cos alpha by 2. So now we have 4 quantities. One is epsilon naught, the other 3 are epsilon 1, 2 and 3 associated with the E1, E2 and E3 respectively, right? Once we have this, you can see that you can replace these quantities, so it's quite clear that if you can represent it in the matrix notation, it becomes even more compact. So suppose we express the matrix epsilon as 3 by 1 column matrix, epsilon 1, epsilon 2, epsilon 3. In some quarters, some literature, they also use a 4 by 1 column matrix where epsilon naught is also included, and you can re-express the direction cosine matrix or rederive in terms of that epsilon as well. For our purposes, we'll just define this epsilon and use epsilon naught explicitly as it is over here. So when we do that, you can quite easily see with a little bit of manipulation that CBA, the direction cosine matrix for rotation of B in A, is now given in terms of the 4 Euler parameters, 3 of which are contained in epsilon and 1 of which is floating as a scalar quantity epsilon naught in this particular form. Again, the epsilon tilde holds the same tilde notation that we have been used to, the antisymmetric version of this column matrix, 3 by 3 antisymmetric matrix. So now the advantage that you see in going from this particular representation where alpha, the angle of rotation, is used explicitly, to this particular rotation where it is used in an implicit fashion through epsilon naught and epsilon, which are functions of alpha, actually functions of linear proportional to sine and cosines of alpha, is the fact that in this particular expression, if you are thinking of epsilons and epsilon naught as the rotation variables, then you see that the direction cosine matrix is only up to quadratic in the rotation parameters. So here it's of course a constant term, here it is coming as squares, and here it is coming as squares, and here also it is coming as squares. So basically the advantage is that whereas in this particular case, if you are to expand this in a power series, for example in alphas, this will in fact be an infinite series. Of course the case is when alpha is very small, then you can neglect the higher order terms and then you could retain only the leading order terms. But we are not interested in such a situation in many situations, and in particular for our own situation where we want to deal with the rigid body like rotations of the cross section to be as large as they need to be. So in such situations it's not possible to curtail a power series, and so a representation like this will make the nonlinear problem a little more tractable compared to a nonlinear problem which is involving an expression like this. So each element of CBA, as I mentioned, is a quadratic polynomial, and the column matrix of angular velocity measures, just like you can express CBA, now we can utilize some of the quantities that we derived or expressions that we derived for quantities in the previous class. For example, the angular velocity, we said that if we want to determine that the angular velocity of B in A, which is a 3 by 1 column matrix, instead we can determine its corresponding antisymmetric matrix tilde with the components expressed along the big B basis as just minus C dot of B in A multiplied by C of A in B, which is the inverse of that or transpose of it, right? So once we know the expression for CBA, it's easy to determine the expression for CAB as well as the time derivative of this and time derivative of this. See, remember that this is consisting of scalar quantities. The 9 elements and the measure numbers are scalar quantities. So when we take the time derivative, that's why there is no A explicitly mentioned over here. It's consisting of scalar quantities. So if we expand that out and do a little bit of manipulation, we'll see that the angular velocity, which is just column matrix basically expressed here, omega 1, omega 2, omega 3, which are the components along B1, B2, B3, the unit vectors fixed in the rigid body B. Okay. So the angular velocity of B in A expressed in the B system is then given in terms of the epsilons and their derivatives in this particular equation. So once again you see that it's basically a quadratic equation, just like what CBA is in terms of the epsilon. So here you have a quadratic term because of the epsilon naught and epsilon dot, again epsilon tilde and epsilon dot, and here again epsilon naught dot with epsilon. So, but 4 Euler parameters not independent, as we've been saying, just like in the case of the E1, E2, E3, we know they are not independent. One of them is given in terms of the other. Similarly, once we have replaced the E's and alpha in terms of the epsilon, we now have 4 Euler parameters, which are epsilon naught, epsilon 1, 2 and 3, and they are related to each other and they satisfy this condition. It's quite easy to see because epsilon naught squared, for example, will involve a cos squared alpha by 2, whereas epsilon transpose into epsilon will involve E1 squared plus E2 squared plus E3 squared into sine squared alpha by 2. Already we know that the sum of the EI squareds are equal to 1 because it's a unit vector, so that's its magnitude. And then basically you have a sine squared alpha, so you have a sine squared alpha plus a cos squared alpha by 2 in both cases. So that basically means that it is equal to 1. So we now have a constraint, just like we had E transpose E is equal to 1. Instead of that we have epsilon transpose epsilon plus epsilon naught squared equal to 1. So we have 4 quantities, epsilon 1, epsilon 2, epsilon 3 and epsilon naught to represent the rotation, knowing pretty well that they are related to each other by means of this particular constraint. So in other words, to avoid the singularity, again you see that there is no singularity appearing here because we are retaining 4 parameters here. It's not that you choose your 4 parameters in any particular way you can avoid the singularity. You have to choose in an appropriate way, then you can avoid the singularity. But when you have only 3, by eliminating the constraint equation, then in all situations you will have a singularity. So now let's talk about the singularity and its control. So usually the temptation is that we want to eliminate one of these 4 parameters amongst epsilon naught to epsilon 3 by using this equation, the constraint equation that we derived in the end of last slide. But the elimination, as we also mentioned and has been shown rigorously by Euler, always introduces a singularity. But depending upon how you eliminate it and what you eliminate, you can control the singularity, and that's what we will show in some example situations. One is a very standard example which is used quite extensively in a lot of beam literature, is what is known as the Rodriguez parameter, introduced by researchers by name Rodriguez and therefore named after him. So Rodriguez parameters are only 3 because they eliminate one of the variables. So all that they do is they take the same 4 Euler parameters and divide the first 3 by the 4th one, which is epsilon naught. So basically, and multiply it by a factor 2, and you will see the reason for that also later when you see where the singularity comes. So it is defined, the theta I, which are only 3 in number, are defined as 2 epsilon I divided by epsilon naught. If you recollect the definition for epsilon naught, it is cosine alpha by 2, whereas the epsilon i's are given by EI sine alpha by 2. So sine by cosine becomes tan alpha by 2 and multiplied by 2 EI, and we can have again a matrix representation, a column matrix representation, so that all the 3 Rodriguez parameters are contained within this single variable theta, which is a matrix variable. Now it's clear that in this particular case, when the argument of tan becomes 90 degrees, then you will have a singularity because tan 90 degrees tends to infinity. So which means that alpha tends to 180 degrees. So at that particular location, or if you want to define it in terms of the Euler parameters, let us say it's when epsilon naught tends to 0, that basically theta I blows up, and that's why you have a singularity when you have eliminated in this particular fashion. Okay, so this singularity is at 0 or at 180 degrees, which is not a big deal for beam analysis, because what we are talking about in that case is a cross section which goes rotates 180 degree about itself, or in other words it turns around and becomes like this, which is very rare for most engineering structures. So it's something that we can typically deal with, and that's why you see that the Rodriguez parameters are quite popular in the beam literature. Next, the direction cosines again can be derived using the expressions that we did with a little bit of algebraic manipulations and replacing the theta i's in terms of the epsilon i's in terms of the theta i's by using this particular equation. And you can see that the direction cosine matrix now gets expressed in terms of this variable theta, which consists of theta 1 to theta 3 in a column. So here again you see that it is quadratic in the numerator and again quadratic in the denominator, but because of this ratio it again brings up the nonlinearity level goes up. So this is, so you have typically two disadvantages always when you're going from the 4-parameter representation to a 3-parameter representation. One is the introduction of the singularity, the other is the nonlinearity level goes up from the simple quadratic level to a higher level. So that's the issue that you have here to manage as well. And again, using the same equation, that minus C dot BA multiplied by CBA gives the omega tilde in the B basis. You can see that the angular velocity of B in A, the body B in the reference frame A expressed in the B basis, can also be expressed purely in terms of the 3 Rodriguez parameters, or rather just the theta column matrix representation, and that again has a quadratic term in the numerator and a quadratic term in the denominator. So this is the closed form analytical expressions that you have for the direction cosine matrix and the angular velocity in terms of the Rodriguez parameters. Now in the limit that alpha tends to 0, the parameters theta I would become the components of the infinitesimal rotation vector. This is quite easy to see because the way the epsilon i's and epsilon naught itself was introduced was in terms of sine alpha by 2 and cos alpha by 2. So sine alpha by 2 would tend to alpha by 2 when alpha is tending to 0, and cos alpha by 2 would tend to 1. And that, if you utilize, you would see that what basically happens is that the theta I would then just become the actual angles about which the rotation has taken place about the 1 direction, the 2 direction and the 3 direction respectively. So that's something which is valid for the very small rotations or infinitesimal rotations. So if all these 3 angles of rotation about the 3 axes are very small in magnitude, then what this would represent is just that those actual angle values of the rotations about the 1, 2, 3 directions, and the order in which it rotated, whether it was rotated about the 1 axis first or about the 3 axis first and then to 1, whatever, really wouldn't matter in the case when you have infinitesimal rotations. But when you have finite rotations, when at least one of these is not small, infinitesimally small, then the order will matter, and it would no longer be directly the rotation vector. Okay, so that's an important thing to remember, that again it's in fact an advantage. Okay, so one is basically that you have, instead of 4 variables to deal with, you have 3. The second advantage that you have is that in the situation where thetas are small, then it is the Rodriguez parameter turns out to be the same as the infinitesimal rotation vector. So these are 2 advantages, but as we said, it also has 2 disadvantages. One is the singularity and the other is the high level of nonlinearity when theta is large.
Sir?
Yeah.
So that order does matter in rotations.
Yes.
Means
Yes.
that superposition is not valid.
Exactly. Exactly. So basically the commutativity is not there. So you rotate about one direction and about another direction. It's not equivalent to rotating about the second direction, then coming and rotating about the first direction. So this again comes from the fact that, for example, we have the rotation, let's say, have an intermediate reference frame. We already talked about that. So we want to rotate from, let's say, A to T and T to B. So then it becomes the total rotation of C of B in A becomes C of B in T multiplied by C of T in A, right? So now you know that two matrices, when they are multiplied, 3 by 3 matrices, matrix A and B multiplying each other is different from a matrix B and A multiplying each other. So the non-commutative nature is what is reflected in this order of rotation also, not being important in determining what is the final orientation. Any other questions on this? Okay. So now we look at a few alternatives to the Rodriguez parameters. As I mentioned already, the Rodriguez parameter is one of the most commonly used set of parameters in representing the rotation in a lot of the beam literature, which involves large rotations of the cross section. But there are alternatives to it. And the alternatives, of course, the room for that or the usage of that is one of the main reasons is the disadvantages that we saw for the Rodriguez parameters in the previous slide. So the first alternative to Rodriguez parameters is not very different from what the Rodriguez parameter itself is, because again, another advantage of the Rodriguez formulation is that it's very useful for analytical derivations because of the way the expressions for omega as well as CBA are in terms of theta. So the Rodriguez formulation is convenient for analytical purposes, but there are better formulations, especially when you don't want to or cannot get analytical closed form solutions and have to move in for a numerical implementation. In such situations, the computational algorithms typically use some small minor modifications of the Rodriguez parameter definitions, especially in flexible multibody dynamics. This is something which is very commonly used because in flexible multibody dynamics systems you will have rotations which are much larger than 180 degrees. So it might during the course of the time of interest, time interval of interest, you will see that the rotations might pass pi radians or 180 degrees, which is basically the singular point for the Rodriguez parameter definition. So we can try to avoid that by very simple ingenious ways. One, for example, is that if you recollect what we had as the definition for the Rodriguez parameters, so what that you do is you change this factor 2 in these two places into 4, okay? So you make it 4 EI tan alpha by 4. So then what happens is the singularity will now be at alpha by 4 equal to 90 degrees, which means that alpha is equal to 360 degrees, which is 2 pi radians are basically turning around itself and becoming the same. So what advantage that does is basically that in a computational algorithm, you can always set some particular parameter, you can estimate it, and once it crosses a particular level, let's say pi radians or something, you can add 2 pi or subtract 2 pi so that you basically, you know that it is one and the same, but basically it avoids that singularity which exists at 2 pi. So that's one of the ways it is handled in computational algorithms. So it moves there, first of all, by changing these two 2's to 4's, it moves the singularity location to 360 degrees from 180 degrees. And in the computational algorithm, as I said, you can test some simple expression to see if the magnitude of alpha at a particular time instant of consideration, you'll be, of course, time marching from one time step to another time step. So at the new time step, if you find that the magnitude of alpha is less than pi, then you basically add 2 pi to basically shift it, and so that you're trying to move it away from reaching 2 pi at the next time step. So that's basically what you're trying to do. So what this will mean is that the orientation you can make sure does not reach that singular point, and therefore one of the main disadvantages which is involved with that kind of a representation is completely avoided. So next we look at another alternative to the Rodriguez parameter. This is kind of quite different from the way the solution was introduced in the previous case. So if any approximation, typically this is a situation where you do not have very large rotations, for example. So in such situations, of course, instead of going to the very extreme case of using just the infinitesimal rotation vector that we talked about, we can use something which is a little more superior to that. So that's basically what we are going to talk about here. If any approximation in terms of the limitation of how much the rotation is going to be, the overall magnitude of rotation, if it has caps, some kind of caps, if it is anticipated in some specific problems, and this is not something we are going to use in our approach, it's just something that I am introducing because this is also commonly used in the beam literature, so you need to be familiar with it. Again, this is something we can use, for example, for local rotations. See, our rotation that we are going to be talking about is made out of two parts. One is basically the overall average rotations of the cross section, and then there is warping, and that warping consists of tiny line elements having small rotations. So basically, because the warping changes along the length, so you take the derivative of that warping with respect to the cross-sectional coordinates, they are like rotations basically, and those rotations are pretty small compared to the overall rotations, the global rotations that are taking place. So in such a situation, just to represent the local rotations, for example, sometimes this can become useful as well. It's not necessary, but you can utilize it for computational efficiencies. So if any, so it's useful to characterize rotations via the so-called finite rotation vector. What we already talked about is the infinitesimal rotation vector. In this, that is, the Rodriguez parameter reduces to the infinitesimal rotation vector. Similarly, in the case when the rotations are finite, so what do you do? So we introduce this vector phi I as the EI, which is the same as the 3 of the 4 Euler parameters, but multiplied by the 4th Euler parameter, which is alpha. So you now have phi I is alpha times EI, and then you represent phi in the form of column matrix once again, consisting of these 3 elements. So once again, we have eliminated a 4th parameter in terms of 3 parameters by expressing it in this particular way, only 3 quantities. So if you do that, you can show that the rotation of the direction cosine matrix for the rotation of B in A is just the exponential of the antisymmetric matrix minus phi tilde. Okay, so again, some of you might be familiar, but for those of you who are not familiar, if you want to determine the exponential or any function for that matter of a matrix, so all that you do is you use the corresponding Taylor series for the scalar quantities, use that for the matrix. So in this case, the exponential, for example, you know that the exponential function is 1 minus x plus x squared by 2, its factorial, etc. So similarly, you can use that in terms of the matrix, and so instead of 1, you have the identity matrix, and 1 plus minus x, so that is basically this itself, so 1 plus x rather. So in this case, because the argument has a minus, you have the minus sign coming over here, and then plus 1 half, which is of course 2 factorial, which is 2 itself, phi tilde times phi tilde, and so on and so forth. So as we in the very first line here said, something like this will be useful if and only if a priori you know that there is some limitation on the rotation magnitude, which means that the following terms are smaller compared to the terms which are already there. So then approximately we can ignore these terms and just take, let's say, these terms, or in some case where it's even smaller, maybe just these 2 terms would be sufficient, etc. Okay. So this is the expression for the direction cosine matrix, and similarly, again going back to the definition for the angular velocity, we can get that also in terms of the finite rotation vector.
So we are eliminating the higher order terms because of this, that will be order of alpha, right? That is why your...
Exactly, right. So this is valid only when alphas are reasonably small, not infinitesimally small, but reasonably small. So for example, I already gave you the example of local rotations.
From the beginning, we are just considering the initial and the final rotation, not the intermediate path. That
exactly.
is why it is in the reasonable range as well. I mean, in order wise.
No, I'm not following your question.
alpha is always in the range of not a very big value or not a infinite small value, because we are considering initial and the final rotation, final the axis, the angle between the final position and the initial position and the final position.
Correct.
So that is within a reasonable range. It is this.
No, so in the case of the rigid body like rotations of the cross section,
This kind of
that is not within reasonable limits. So it can go to any value, any large value it wants. So
But
in such a situation, you cannot have this kind of a representation. On the
it
other
is 0
hand,
to 2 pi, right, sir?
pardon me?
It is the value between 0 to 2 pi,
Right.
because it doesn't follow the intermediate path, right?
Yeah, in the case where you had, let's say, that definition as 4 with alpha by 4, so then you tan alpha by 4, then in such a situation you have the singularity at 2 pi, and that's something which is quite reasonable even for the rigid body like rotations of the cross section. But what I'm talking about now is something for much smaller values of the angles, not even pi or 2 pi, but much smaller than that. So these are things which cannot be used for rigid body like rotations of the cross section. They can be used, for example, for the local rotations. So that's the example that I gave. Again, all of these things that we are talking about today are valid for any kind of rotations.
Yeah.
Though our intended application is for beams, they are valid for any rigid body like rotations. So there might be situations that you can always find where the rotations are limited. Let us again, what is the value would again depend upon what is the quantity that you are eventually trying to determine, and what tolerance levels you have for them, etc. Okay.
That means, sir, this series where will truncate that will depend on the value of alpha, right, sir?
Exactly. Right. So this is the expression you have for the angular velocity expressed as a matrix, column matrix in the big B basis, and then you basically again you have terms involving the phi dots and the alphas as well, and typically first few terms of this is utilized in determining, and of course it can be expressed in a simpler fashion. So this is, for example, what you would take in many situations, especially when you're dealing with local rotations. We will see one of the applications would be to use this formula for omega and CBA. Okay, so with this we'll just make a conclusion on the rigid body rotation that we have been studying. And the reason why we took it up as well, not only the rigid body rotations but also kinematics in general. For example, we introduced in the previous class the expressions for the velocities, how to determine velocity of one point on a rigid body which is fixed if we know the velocity of another fixed point, or how to determine the velocity of point which is moving on a rigid body. So in all those things that we did for rigid body kinematics, it basically we introduced the fundamentals of that. Those of you who are interested can go into some of Kane's books. Kane, K-A-N-E, is one of the professors from Stanford University. He has written a lot of nice, interesting books based on rigid body dynamics, especially applied to spacecrafts, etc. So in many of those books you will find derivations for many of the equations that we listed out as results over here. And of course the reason why we did this rigid body kinematics is the fact that in intermediate form of the derivation we are considering the average motions of the cross section as the rigid body like motions, and there it will be useful, and some of the expressions that we had in the previous slide, for example, would be even useful while dealing with the warping. So what we need to do is to build upon this foundation that we have for rigid body dynamics and to develop eventually the kinematics of the beam theory, because as we know the whole beam theory involves, just like any structural mechanics problem, three aspects, because it has to connect the four variables that we have already been talking about. So it needs the constitutive law, it needs the kinematics, and it needs the equilibrium equations. So the kinematics part of it very strongly depends upon understanding the fundamentals of the rigid body kinematics, because of the fact that the entire beam problem breaks up into parts, and one of those parts involves the rigid body like motions of the cross section. So what we will do next is to utilize these equations that we have developed in understanding rigid bodies, both for determining the velocity as well as the strain displacement relationship. The velocities are also of course going to depend upon the displacements and the rotations which are involved. The displacements, of course, the translations of the cross section, and the rotations is the rigid body like rotations of the cross section, and in turn you would have the warping variables, which again can be divided into two parts as the for example, if you're talking about a strip like this, then basically you can talk of the average warping along the thickness as one of the translation variables of those line elements, and then you can talk of the rotations of those as the local rotations, the rotation about the one axis and the rotation about the two axis will both be local rotations. So all of those can basically be tackled by utilizing the results that we presented in today's class as well as the last couple of classes. So first of all, we'll look at some basic aspects before we get into the equations for the beam kinematics. First of all, how strain can and should be represented for a beam. Again, for the purposes that we are interested, there are many alternatives. Just like for rotation, we saw so many different alternatives in terms of how we can parameterize the rotation. Similarly, there are many different ways of expressing the strain. In fact, one of the future classes will look at various strain definitions, and we will see which is most appropriate or useful for our own purpose. But basically, in today's class, we will look at the more preliminary aspects of how strain can and should be represented for the beam. It's helpful to discuss beam deformation in terms of two geometric features of the beam, as you are already aware. One is, of course, the reference line or the reference curve in the case of initially curved and twisted beams. And then, of course, the cross-sectional reference plane. Again, what we do for a generic cross-section, what we call as the reference cross-section, will be something which is valid for the entire beam, especially if it's a beam which has the same cross-section throughout. Even if it has different cross-sections throughout, it can so happen that it can be of the same class. For example, it could be, let's say, an I-beam, but it might have different flange lengths along the span, so typically causing a taper in the wing, for example. But even in such situations, we can use the same results but with different numerical values for the flange width, for example, along the length, etc. So typically the cross-sectional analysis, though it appears that you will have to do in reality at infinite locations because there are infinite points on the reference curve, it's usually not necessary to do so. You can do it in a finite number of cross sections, even if the cross section is typically varying. So that's basically the analysis at the cross sectional reference plane. The beam deformation is describable in terms of, again, the deflection of the reference line, which is basically what we represented as the variable u, if you remember the picture that or schematic that we had for the beam kinematics. We'll repeat that shortly. Then, of course, the motion and deformation of the reference cross-section plane. So basically the reference line from its initial configuration has moved elsewhere, and then along with that the cross-section has moved, by which we mean, because it's like moving like a rigid body, because we are only considering its average motions as of now. So basically it has the three translations and the three rotations. And then, of course, you have the motion and deformation of the cross-section, which can be thought of as, again, decomposed in this way. First of all, the rigid body translation and rotation, that I just talked about, of the reference cross-sectional plane of the undeformed beam. And then, compared to this, it is a relatively small elastic deformation which is superimposed on it, which we call as the warping. The reason why this has to be small is not an additional assumption, but it's a direct fallout of the fact that the material out of which the beam is made cannot take large strains. It fails at a strain which is small compared to unity, and therefore it turns out that the elastic deformations of the cross section, which is the warping, cannot be large. So this is relatively small elastic deformations which are superimposed upon the rigid body motions. Next we have we can group the rigid translation and rotation of the cross-sectional frame with the beam global deformation. So here we saw that the overall motion is basically composed of two parts, the deflection of the reference line and the motion and deformation of the reference cross-section plane. Now we will keep the deformation separate and we'll move this motion of the reference cross-section into this part, because this as well as this are large, so these can be considered simultaneously. So that's basically what we will do. So that rigid body like translations and rotations, which is what is here, will go into this, and the deformation is something which can be tackled separately. Yes, please.
Anyway, the cross section has to move along with the reference line. So why do we have two different names for it? Reference line, wherever it goes, cross section will have to follow that.
That is right in terms of the translations, but in terms of the rotations, for example, it could be different, and that is the reason why the normal to the cross section doesn't remain normal, whereas the tangential vector for the reference curve can be at an angle with respect to the deformed cross section now, right? So in that sense there is a slight difference between those two. Okay, so one is basically the rigid body translation, which has brought the reference curve from its undeformed configuration to the deformed configuration. You are right perfectly that the rigid body, the like cross section, also moves along with it and comes to that position. But in terms of the rotation, it has an additional degrees of freedom compared to what the reference curve alone has. So we group the rigid, as I said, translation and rotation of the cross-section frame with the global deformation. So that's basically what we do. We move this part there, and then the deformation of the cross-section is what alone remains, and that can be classified as a local deformation or what we call as warping. And once again, that warping we will see breaks up into two parts, which is basically the averages, especially for thin the class T and class S beams. It breaks up into two parts. One is basically along the thickness. If we talk about a line element, it has its average motions, which we continue to call as warping, and its rotations, average rotations, which we will call as the local rotation.
So repeat the last one, please, sir. How do you decompose this warping into parts?
Oh yeah. So basically, again, these are things which are going to happen automatically. So for example, let's take the class S beam. So in the class S beam, we have this cross section, let us say, which is thin rectangular cross section, to keep things simple, to demonstrate. But basically, this is something which is valid for any thin cross sections for class T beams as well. Okay, so now, if for example, it could be the flange of an I section also, need not be on necessarily a rectangular cross section. Okay, so now if we take this rectangular cross section, now if you take at some location a line element which is perpendicular to the plane, if you're thinking of this as a plate, let us say. Okay, so there's a line element over here. Now warping is such that it is a function of x1, x2 and x3 apart from time. Okay, all three spatial coordinates. Now we have already fixed the cross section, so which means x1 is fixed. So at that cross section it is a function of x2 and x3, right? Now if you're talking about a line element over here, I can average out the displacements due to warping basically on that line element, which means I can integrate with respect to x3, which is the thickness coordinate, from minus h by 2 to plus h by 2, if h is the thickness of this strip, and then divide by h. So I get the average, right? Similarly, I can take its derivative with respect to, let's say, x2, and then I can take its average similarly, that is, integrate from minus h by 2 to plus h by 2 and divide by h. Okay, so now because that let us say we are talking about the warping W1. Okay, so W1 is basically this cross section coming out. Okay, so it is basically becoming like this. Okay, and it is over and above the average displacements that have already happened for the cross section. Now at a particular location, that is a line element, can become something like this. Okay, So now that can be thought of as basically an average translation of that line element and an average rotation basically in this direction as well as in this direction, right?
That
So
means
of each line, and the line element here can rotate by a different amount from a line element here. So in other words, the cross section is still changing its shape and size because of these rotations as well. So in other words, it is not part of the so-called rigid body like rotations of the cross section, but it is part of the so-called rigid body like rotations of a line element. So in other words, what we are doing is we have moved from a, let's say, a 3D to a 2D problem, and you're going from a 2D to a 1D kind of a problem. So you're going in a two-step process. In such a situation, you can basically represent that. But this concept of local rotation is something which is valid even if you're not doing this two-step process and going directly from 3D to 1D. You still have this concept, so-called concept of local rotations, where in an arbitrary shaped cross-section, something like this, in a class R beam, you have a cross-section like this. You can take any two points on that cross-section which are fairly close to each other, and then basically draw a line connecting them, and basically you can think of all the warpings on that line basically being averaged out, and their derivatives with respect to the cross-sectional coordinates also being averaged out. Then the derivatives averaged out will give the rotation of that line element. You just think of a very small line element over there connecting 2 points infinitesimally close to each other. So that line element can move, translate, and it can rotate.
move in X
Apart from that, of
direction.
course, it can have additional deformations which make it to warp as well within itself.
Yeah,
So
that means in this case, that line it was there, it can warp in this direction x1 and have two additional rotation as well. Right?
exactly. So W1, comma 2 and W1, comma 3.
Yeah,
Right.
and in this case of S class, you have mentioned that we will have two lines, right, sir? One in X or
No, so these are concepts which are valid for whether it is S class, T class,
oh,
or
same line, same
R
line.
class. It's
that
the same
will-
same thing.
Okay.
Here it was basically easier to illustrate, so that's why I took up this
Okay,
example
okay,
first. But it's something which is generally valid across the classes, S, T, or R. In all these situations, you can always define the so-called local rotations, basically in terms of averaged out rotations of a line element formed by joining 2 points. In this case, I could talk about a line element which is basically running through the cross section because of the fact that the cross section's thickness is small compared to the width. So that's why I talked about the entire line. Whereas in an art class, I cannot talk about an entire line like that. That's no longer a so-called local rotation. You have to talk about a line which is connecting 2 points which are close to each other, which is in fact
in this
close
S
to each
class,
other.
in this S class, that means sir, along if it is x2, that width I suppose that is x2. So there is several lines, right, sir?
Exactly, right.
So-
and each one of them can have different rotations and different translations.
Okay.
Right?
So okay, sir. No, sir.
So what is the goal that we want to achieve by applying this so-called decompositions that we talked about in the previous slide is to obtain simple matrix expression for the beam strain components. So eventually we want to derive the expressions for the 3D strains at any material point, and in doing that we will utilize those decompositions we talked about in the previous slide. So in which the global displacement and the rotation may be large, and the only restrictions are on the magnitude of the strain and therefore on the warping and therefore on the local rotation. So the local rotation, as I just described more figuratively here, it is expressed in words, is the rotation of the material elements in the reference cross-section plane with respect to the deformed beam cross-section reference plane. So basically there is an overall rotation which has taken place, average rotation of the cross-section. This is over and above that, it is not included in that. That's basically what it means. And this is of course entirely induced by the cross-sectional deformation, so it's not separate from warping. It is one aspect of the warping, okay? It's because of warping that it is happening, but local rotation by itself does not contain all of the warping. There is more to warping than local rotations alone.
Sir,
Yeah.
So we talked about breaking up the warping again into average
Yeah.
translations and rotations,
Right.
and then separating out some portion of that as let's say second order warping kind of. So then this restriction on magnitudes of strains and local rotation that we're talking about applies to the first warping that we did. I mean,
It applies to the total. So it applies to the total, and because of the fact it applies to each one of those individual components as well.
so those if the very first warpings were broken up into some rigid body translations and rotations again, then this local rotation would apply on rigid body rotation as well.
I'm not following you.
So to start with, we separated the total deformation of the beam cross section by some rigid body rotation and translation and warping,
Correct.
and then we broke up the warping again into rigid body rotations and translations of small infinitesimal line elements.
Okay.
Then this restriction on the local rotation applies to the warpings in the second step or in the first step. I mean.
First time.
See, the restrictions apply on warping, right? See, the restrictions are not something which are assumed, but follow from the fact that the strain is small. So when we will derive the expressions for the strain and in terms of the overall warping, and then we can express the expression for the strain in terms of those components of warping, including local rotation. So from that expression itself, we can determine, because the total strain has to be small, what is the order of magnitude of those local rotations. So that will enable us to determine the orders of, or estimate the orders of magnitude. And of course, those are variables, unknown quantities, which we will solve for when we get the governing differential equations using the Euler-Lagrange equations of the calculus of variations. And when we solve for it, we can go back and compare with the estimate that we made for the local rotations, and then we can arrive at the appropriate conclusions. So, and in most situations, this so happens that the local rotations will be small compared to much smaller compared to the global rotations of the cross section, because of the fact that if they happen to be large, for example, the components that we are talking about rotations are W1, 3. That will directly contribute to a 3D strain capital gamma subscript 1, 3. W1, 3. So if W1, 3 a local rotation, which is basically how W1 changes along the 3 directions. So basically it's a rotation like this of the line element, right? So that local rotation, if it is very large, what it will do is it will make the strain gamma 1, 3 very large, which would make the material fail, and therefore the beam not to be able to hold the load. So what we are dealing with is a healthy beam, and therefore you have a restriction on the W1, 3 and therefore on the local rotation. Similarly, you can extend that idea with the other local rotations as well.
So is this restriction also applicable in case of hyperelastic material as well?
Hyperelastic materials, the strain that you have to talk about will not be,
they'll have
see,
their own
typically the
limits.
strain that you have restriction over is basically for the elastic materials. For hyperelastic materials, there are some materials which can go all the way up to 400% strain, etc. So in that case, the maximum strain epsilon is not small quantity compared to unity. So you have to completely drop that out and deal only with the geometric small parameters that you have. So in the variational asymptotic method. So many of these conclusions that we are making will not hold for hyperelastic materials. But again, within hyperelastic materials, there are a class of materials which can take strains only up to of the order of 20%, 30% strains. Okay. So in such situations, we can still deal with epsilon as a small parameter compared to unity, because 0.2 or 0.3 is small compared to unity. But the interrelation between the small parameters, because remember there are multiple small parameters here. One is the strain, the other is basically the geometric small parameters like the thickness to width ratio, width to length ratio, etc. Now the relative orders of magnitude of these small parameters will change for hyperelastic materials, and therefore the theory that you derive and the results of the theory will also change. Okay,
Or
but
approximation.
it becomes very, very difficult for you to derive a theory for hyperelastic material, beams made out of hyperelastic materials which can take strains of the order of 1 or typically like 400%, etc. In such situations, you have to completely eliminate that small parameter and deal only with the geometric small parameters. So many of these advantages that we have in dropping off terms because of the fact that it is a small strain will not occur there. Not that it cannot be done, it's a much more complicated process compared to the situation when strains are either small or are moderate, as in the case of 20 to 30%.
This ordered approximation won't be that easy, which are possible in this case of elastic materials. Right?
That's correct, yeah. Yeah. So local rotation we already saw is basically one of the aspects of warping. Vectors and tensors are resolved along orthogonal triads of base vectors which are associated with the cross-sectional reference frames of undeformed and deformed beams. So we already introduced in the schematic a small B1, B2, B3 system and a capital B1, B2, B3 system. So there will be many other vectors and tensors which are associated, let's say for example the displacement, etc. So each one of those are the tensors like the strain tensor, etc. And each one of them, when we want to express them in the form of components, they have to be expressed in the case of vectors as a single basis and in the case of dyadics as a dual basis. And when we resolve them, we will basically utilize those small B1, B2, B3 system and a big B1, B2, B3 system in order to do that. And because we are dealing with initially curved and twisted beams, a curvilinear coordinate system is usually more convenient. And even if we are not dealing with, let's say, initially curved and twisted beams, because of the fact that the rotations we are allowing for are very large and the translations are large, it so happens that the deformed configuration is highly curved and twisted. So even in such a situation, a curvilinear coordinate might be quite useful. But in the approach that we are taking, though the curvilinear coordinate system is natural to the beam problem, there are certain complications which are associated with the curvilinear coordinate system. Not that it cannot be done, it can be done. But for our purposes, we will just restrict ourselves to a Cartesian system, and still we should be able to deal with such large rotations as well as initial curvatures and twists. So local rotation components appear explicitly in resulting strain expressions, facilitating the treatment of beams of various classes. So that's where you will see a difference. We will start off in a general sense to derive the overall beam theory, especially the beam kinematics as we are talking about here, and eventually we'll express the strains, the 3D strains, apart from other quantities in terms of the local rotations as well. And when we do that, we know that, for example, in the by the very expressions, we can show that the local rotations will be larger in the case of S-class and T-class beams, whereas it will be much smaller in the case of R-class beams. If they are not small in the case of R-class beams, it so happens that the strains that result will be large, and therefore from the fact that the strains are small, we argue back to show that they are small in the case of R-class beams, whereas they can be large in the case of S-class and T-class beams. And in fact, apart from the way we classified beams earlier as RS and T based on, let us say, the curvatures due to bending, the flexural curvatures kappa 2 and kappa 3, and the torsional curvature kappa 1, having different relative orders of magnitude with respect to each other, instead of that classification, we can classify using the local rotations orders of magnitude as well, and they turn out to be equivalent ways of classifying the beams. Next, the theory used to obtain the kinematical relations for all possible deformations of initially curved and twisted beams. So whatever theory we derive using this particular approach will be generally applicable for all initially twisted and curved beams, and of course we are using the beam in a very general sense, not only bending but axial forces. They could be tensile or compressive, and the torque, of course, causing that twist. So next we'll talk about the concept of rotation and decomposition, because remember we've been talking about two different types of rotations here. One is the overall rotation of the cross section, and then there is the local rotation. So if we understand the concepts of rotation and decomposition, when we reach there it will be easier for us to decompose it into two parts. So first of all, the rotation we'll express mostly in words over here, eventually bring in the equations. So rotation is separated into two parts. The first is the arbitrarily large global rotation, which is associated with the cross-sectional frame of the deformed beam. And then there's moderately small local rotation, which is associated with the warping and the transverse shear strain. So again, we already mentioned that this transverse shear strain, there are two ways of handling it. One is to lump it along with the rigid body-like motions of the cross-section. The other is to lump it along with the warping. When it is lumped along with the warping, that can be considered as a local rotation as well, okay, because it is something which is associated with warping. Any rotation which is associated with warping we are calling as the local rotation. But it's basically eventually the final 3D recovery would be the same irrespective of which way you approach the problem. It's just a matter of convenience. For certain problems that we do it in this way, and other problems we can put the transverse shear as part of the global rotation that is in the first bulleted item here. Physically reasonable assumptions would be small strain because of the materials that we use, and we would see that the moderate local rotation is not an additional assumption but a fallout of the small strain, which will become apparent when we see the expression for the overall 3D strain. So what this means is a rather simple kinematical expression which is valid for arbitrarily large deflection of the beam reference line. In other words, the displacements that we are talking about of the cross section, the translations could be very large, and large rotations of the cross-sectional reference frame as well. And the introduction of dyadics into the analysis, which is what we will do, will significantly simplify the derivation process. But for those of us who are not comfortable with dyadics, it's not necessary to actually bring in the dyadics. And also, if our only intention is not to understand the derivation rigorously but just to use the final results for our own problems, even then the final results, because they're going to be expressed purely in matrix forms, it may not be necessary for those of you who are going to just use it in an application scenario to understand the dyadics. It's only for the derivation, and that too to make the derivation look compact, that we need the aspects of dyadics that we've already introduced in the previous classes. So as I said, the final expression obtained does not require the knowledge of tensors at all, because it will be purely in matrix representation. So now we come back to the beam schematic of the kinematics, which is the beam geometry in the undeformed and the deformed state. You recollect, so the beam idealized as a reference line, which we call as R over here, this R, and x1 is the length along that R, which you see over here within the undeformed beam, and x alpha is of course the coordinates which are introduced within the cross section. So lengths along straight lines which are perpendicular to R. And of course there in some situations, as we already talked about, for example swept wings, it might be convenient not necessarily to have this perpendicular, so that kind of a restriction can be removed as well. Okay, it's for keeping things simple in the beginning that we are putting this restriction. It's not necessary. The beam particles are located by R hat, so that's basically from some point in another reference frame A, which could be the aircraft fixed frame or helicopter fixed frame, whose motion in an inertial reference frame is already known, because we know the dynamics of flight dynamics of a flying vehicle. And so basically from that point fixed in the reference frame A, we have this arbitrary material point located by R hat as a function of all three spatial coordinates apart from time. The Greek indices, as we already mentioned, will vary between alpha, beta, gamma, etc. If we use as subscripts, will vary between 2 and 3, which are basically the cross-sectional coordinates. Remember x2 and x3. That's why you have b2 and b3 there as well. And the Latin indices like I, J, K, etc. will vary between 1, 2 and 3. And the repeated indices will be summed over their ranges by default. So now we will set up a motivation here for some of the aspects that we have to derive mathematically. Why do we need some of those quantities? Okay. In the next class, we'll be looking at the various quantities that we want to derive expressions for mathematically. So we'll see where each one of them fits into the bigger piece of the puzzle as far as beam kinematics is concerned. So kinematics obviously are things which involve, let's say, the strain and displacement. If you remember that large chart that we have of 4 variables and 3 quantities. So it's basically the last set of equations to relate the strain and the displacement. And in the case of dynamics, instead of strain, you have velocities and angular velocities, etc. Okay, so it basically needs to bring in that relationship. So it first of all requires strains, expressions for the 3D strains, and which in turn needs the so-called deformation gradient tensor. So if we want to derive the strain in a rigorous manner, we need a concept called the deformation gradient tensor expressed in a mixed basis. Okay, we will see that just like any other dyadic, it is basically something which needs 2 sets of bases in order to be expressed in its numerical components or analytical closed form components, measure numbers. And for that we typically take 2 different bases. In our case, we already introduced these 2 small b and big B system that are associated with the undeformed configuration and the deformed configuration. So those are the 2 bases that we will typically use to get the deformation gradient tensor expanded. And the reason why we need that is the strain is going to be described in terms of the DGT, and therefore we need the DGT. Now suppose we want to derive the deformation gradient tensor, we need certain other quantities. So this deformation gradient tensor in turn is defined in terms of the so-called covariant and contravariant basis vectors. So we'll spend a major part of the first half of next class in understanding these concepts of covariant and contravariant basis vectors, because they are essential to derive the deformation gradient tensor and therefore the strains. And if we want to understand the covariant and contravariant basis vectors, in most case situations, these are not the kind of systems or unit vectors that we have, like let's say the small b1, b2, b3 or big b1, b2, b3, etc., which we have been dealing with, which are orthonormal sets of unit vectors, or in other words, bi dot bj is equal to delta ij, the Kronecker delta. So that is something which is orthonormal. But in general, the covariant and contravariant basis vectors will not be orthonormal. In other words, the 3 vectors which are used as the basis need not necessarily be perpendicular to each other, and they need not be all unit vectors as well. Okay, so in such a situation, how do we deal with? So in order to understand that, we have to introduce the concept of non-orthonormal basis. So that's what we will first do. So I think we do have time to just go through that non-orthonormal basis first, and in the next class we'll go into the covariant and contravariant basis vectors. Now this is basically what we are talking about here. Suppose we have an axis x, y and z, and let's say we have vectors along that, not necessarily unit vectors. In case they were unit vectors and they were these x, y and z were let's say an orthonormal basis, then they would be mutually perpendicular to each other, and each of them would have a magnitude 1. And in that case, if you have the vector along this as I, j and k, then I cross j would be equal to k, and j cross k would be equal to I, etc. Right? So that is quite obvious, because that is what orthonormality leads to. But in a situation where each one of them I, j and k are not necessarily unit vectors and not necessarily mutually perpendicular to each other, it is always possible to determine another set of quantities I star along this x star, j star along y star and k star along z star, so that though I cross j is not equal to k, it is equal to k star, which is the vector along this. And again, these I star, j star and k star are not orthogonal to each other, and they are not necessarily unit vectors in the general case. So, but it is still possible to determine those three vectors as long as these are not collinear, that is, they are not parallel to each other. It is still possible to determine these three in such a way that I cross j will be equal to k star, j cross k will be equal to I star, and k cross I will be equal to j star. So in other words, these two sets that you have, one could be, let's say, the covariant basis vector. What is covariant, what is contravariant, we'll come to later. But basically one set could be the covariant, the other could be the contravariant. Between them, they form a set in such a way that something like orthonormality can be achieved. So that's basically what we'll try to do. And any arbitrary vector v, if we take, we can express that arbitrary vector v either in terms of the ij case or in terms of the I star, j star, k star. So if we express it in terms of ijk, then we express it its measure numbers as a1, a2, a3 with the numbers being superscripts, let us say. Okay. And in the other situation, if we want to express it in terms of I star, j star and k star, then the measure numbers become again a1, a2, a3, but in general the numbers will not be equal to each other, and to distinguish that we will put them as subscripts a1, a2 and a3. Now what we call these are, suppose we call these ijk as the covariant basis vectors, then these measure numbers that you have here are called as contravariant measure numbers. And similarly here, if the I star, j star and k star are the contravariant basis vectors, then these a subscript 1, 2 and 3 become the covariant measure numbers. So covariant measure numbers go with the contravariant basis vectors, and the contravariant measure numbers go with the covariant basis vectors. So this is something we will expand out in a more mathematical sense in the next class, but all that it basically does is basically you have, let's say, coordinate measures. So let's say you have x1 and x2, and you have these coordinate curves where each one of them is equal to a particular value. Along all points on this line, x1 is equal to alpha. Similarly, along all points on this line, x2 is equal to beta. Now suppose x1 changes by a value plus delta, then basically you get a new coordinate curve over here where x1 is equal to alpha plus delta. Similarly, you get a new curve over here, and similarly in the case of beta, suppose we in the case of x2, suppose from its original value of beta we can either increase or decrease by delta, then you get a new set of coordinate curves. Now suppose we have an arbitrary vector, let us say a over here. We can express, just like we had an arbitrary vector v, which we could express in two different ways using covariant and contravariant basis vectors. Similarly, this a can be expressed in terms of two different sets of quantities, and that is, one is which are tangential to these coordinate curves, which are what are called as the covariant basis vectors, just like what we had here, and the other are perpendicular to the coordinate surfaces which are formed by these coordinate curves and which are represented by these superscripts a1 and a2 over here. So these two are basically the contravariant basis vectors, which you see are perpendicular to the coordinate surfaces, whereas these are the tangential. Sorry, this is the tangential. So these two are the tangential. Sorry, E1 and E2 are the covariant basis vectors which are tangential to the coordinate curves, whereas E superscript 1 and E superscript 2 are perpendicular to those coordinate curves and form the contravariant base vectors, and correspondingly their measure numbers are the other way around. Okay, so I think.
So what is this beta and alpha beta means?
Sorry.
This alpha and beta, x2 and x1.
Yeah.
They are
So see, these are coordinate curves where x1 and x2 take on particular values. Okay. So if x1 takes on a value alpha, then you have all those points
Okay.
joined together. So the loci of points on which x1 takes the value alpha. Okay. So say in the case of just a Cartesian coordinate system, it would be just, let's say, the axis or lines parallel to the axis, right?
Sir, Z star is perpendicular to X star and Y star, is it?
Please repeat that.
Z star is perpendicular to X star and Y star. Z star, this.
No, not necessarily. It's just shown in here like that, but it's not necessarily perpendicular to. These are three vectors which are not parallel to each other, and similarly these are three vectors in general which are not parallel to each other and could hold any angle with respect to these. Okay, it's just shown like that in this particular schematic.
But we
So
define
then,
I cross J.
Oh yeah, sorry. Yeah.
So one has to be normal, right?
So it will be,
Z in
see,
Y.
Z star will be perpendicular
X
to
and
the
Y.
plane of x and
X
y.
and Y.
The plane
Yeah,
of x
yeah,
and y. That's
that's
correct.
it.
You're right. And similarly, the others as well. Yeah. Any other questions? Okay, then we'll stop the class for today and continue.